Well, good morning, everyone. My name is Richard Gordon, and I'm Technical Director for the Spring Manufacturers Institute. And I'd like to welcome you to this special webinar on shot peening. I'm delighted that you could be with us today. We've got several students with us from prior SMI webinars. Welcome to you all. The training course instructor is David Breuer, Director of Sales North America at Curtiss-Wright Surface Technologies. Dave has been with Curtiss-Wright for 26 years. He is a recognized subject matter expert on shot peening and has presented at SMI educational events in the past. He was a featured speaker at the International Conference on Shot Peening that was held last September at Purdue University. David's company is providing support to the SMI fatigue test program by providing shot peening of test springs through SMI member company Associated Metal Forming Technologies. This webinar is being recorded and will be available to SMI members on the SMI website. First, I'd like to provide some background information about the Spring Manufacturers Institute that some of you may be aware of and others may not. The mission of SMI is to serve, support, and educate North American spring manufacturers to assure competitiveness in world markets. SMI was founded in 1933 when 33 companies that manufacture springs and their associate suppliers joined together. Members of SMI work together to meet key issues in the industry worldwide in areas such as quality, materials, technology, and government regulations. SMI services include our quarterly magazine Springs, a variety of technical publications, spring design software, industry data, seminars, meetings, safety and regulatory compliance support, and of course, technical assistance and training. Our technical assistance to members includes answering questions about fatigue life and fatigue testing, corrosion problems, materials related problems, but also development opportunities, process related problems, interpretation of standards. We have a formalized failure analysis program and have completed over 30 projects since we started the program back up in 2018. And again, we have our training and spring design assistance. Our training session for today is planned as a 45-minute presentation followed by 15 minutes questions and answers. At the end of the class, we'll ask you to complete the course evaluation that was sent to you via SurveyMonkey. If you didn't receive the course evaluation SurveyMonkey, let me know in the chat and I'll send one to you. We certainly look forward to your feedback. In terms of housekeeping, we ask that you place your computer on mute. Ask questions as needed during the presentation, either by unmuting your microphone or via the chat icon on the Microsoft Teams screen. And if you do use the chat, please respond to everyone so that our fellow students can see the questions. And as I said, David will address questions both during the presentation and at the end of the presentation. And of course, if you need to increase the magnification on your screen, you can do that by pressing that plus icon at the bottom. So why is the subject of shot peening important to spring designers and manufacturers? In our advanced spring design class 301, Springs Fatigue, we discuss failures that occur in springs. As we categorize spring failures that we see in our failure analysis work, there are several mechanisms that are involved. And what SMI has found and others have reported is that over 50% of failures are due to fatigue. Now, fatigue damage is caused by a combination of actions of cyclic stress, microscopic plastic strain, and tensile or shear stress. What we've learned is a fatigue fracture occurs in 3 stages. crack initiation, crack propagation, and then catastrophic fracture of the remaining cross-section. So where do cracks initiate? Cracks typically initiate at the highest stress location. We learned that the highest stress location on a spring is at the surface, and for compression springs, the highest stress location is at the inside diameter due to the spring helix. So our mission or goal is to increase resistance to crack initiation. Again, in our fatigue class, we discussed several methods to improve fatigue life of springs. These include modifying the spring design, selecting a higher strength material, selecting a higher quality material, either with an improved surface or with improved micro cleanliness. We can preset compression springs, and of course, shot peening is one of our most important things we can do. Electropolishing and low temperature nitriding of certain grades. So today we've got the opportunity to explore shot peening. So now I'd like to turn the presentation over to your instructor for this class, David Breuer, Director of Sales North America at Curtiss-Wright Surface Technologies.
Thank you very much, Mr. Gordon. I am going to share my screen and then put the presentation up. And you should see it in a second or two. So yeah, this is the only slide that has any type of commercial value to it. So I work for Metal Improvement Company, which is a subsidiary of Curtiss-Wright. And we do several different technologies. I'm going to focus on controlled shot peening today. We also provide several different types of coatings, from solid film lubricants, thermal spray, Parylene, and then we have an analytical services arm. And we also do isotropic finishing. So I'm going to jump in, and as was mentioned before, if you have questions, just please bring those up as we go along. So I believe Richard did a pretty good description of metal fatigue. How I define it is it's tens of thousands to hundreds of thousands to millions of start-stop fatigue cycles, and what causes the failure is the tensile stress of that fatigue cycle. So this is a pretty good sized shaft here, and this is like a pretty nice looking fatigue surface for like teaching a class. So what happens is that metal fatigue starts slowly. So the fatigue crack did start here at the 3 o'clock position. So let's say it took 250,000 cycles for the fatigue crack to start. When the crack is very shallow, it grows slowly. So as the crack is growing into the surface like this, again, it grows slowly while the crack is shallow, and then once the crack gets to a certain depth, it starts to grow more and more rapidly. So let's say it took 250,000 cycles to start. It took 250,000 cycles to grow to this deep, and as the crack grows faster, let's say it took 250,000 cycles to traverse across the cross section until there was so little left, it just ripped off the rest of it, the remaining portion. So one way I like to look at shot peening, applied stress and shot peening stresses. If you look at your forearm, and let's just say you take a fingernail and you pretend to put a little cut or scratch in that. Now, if you grab that little scratch on both sides and you stretch and pull, that's kind of like a cyclic tensile stress trying to open up the surface. And then you can see how any type of cut or scratch you have is going to get bigger by continuing to stretch and pull on it. So now if you were to change direction and pinch that little scratch shut, that's kind of what shot peening is doing to the surface, is it's compressing and squeezing the surface. So in essence is that the shot peening residual stresses are the opposite direction of the tensile stresses that cause failure. So with us being a shot peening job shop, we stock a lot of different media for a lot of different situations. And so some different materials we have is we have different harnesses of steel shot. We have peening grade glass beads, ceramic and stainless steel, and a pretty wide variety of shot sizes. The smallest would be about a 2/1000 diameter glass bead up to an 1/8 inch BB. So depending upon the material of the application, which will help dictate what the material of the shot is, and the geometry that needs peening, which will dictate the size of the media. And then, so of course you can see the media strikes the surface here. And then when the media strikes the surface here, it does leave a dimple For very hard surfaces, it can be challenging to see the dimple. And then on softer materials like aluminum, you can see them pretty easily with the naked eye. So when we look at this dimple here, unlike a more of a technical basis, this is actually a zone of residual compressive stress here. So remember, this residual stress, this is in the part with no external loads. So when the BB or the shot media strikes a surface at the point of impact, it physically elongates and stretches this impacted area to the point where it yields in tension, and then the media bounces off the surface. And then the surface tries to restore itself, if you will. It's trying to push that dimple out. And then in the attempt to restore itself, it leaves that surface in residual compression. Are there any questions or comments on that? So if we were to measure the residual stress, this graph here just happens to be for a spring wire, a 260 KSI spring wire. So this graph plots residual stress on the vertical axis as a function of depth here. So of course 0 is the surface, and this is going into the depth. So compressive stresses are defined as negative. So more negative implies more compressive stress magnitude. And some of these variables are fairly predictable. Like the peak compressive stress from shot peening is usually going to be about 1 or 2 thousandths below the surface. This is going to be about 100. This is going to be about 55% of the tensile strength. So this spring has a tensile strength of 260 KSI. So if you take 55% of that, that's going to be about 150 KSI. And then here, where the compressive stress crosses the neutral axis, which in this case is 7 thousandths deep, this is also fairly easy to predict. Then the last variable is the surface compressive stress, which is almost always less than subsurface. And generally you want this more compressed, and this can be improved with a secondary dual peen. However, a single peen does work well for 90% of the applications. And if there's aren't any questions, I'll go to the next slide. So before I had mentioned that, when you look at, what the part experiences, it's actually the summation of the applied stress plus the residual stress equals the net stress or the total stress of the part. So if we take this beam here and we apply a load at these 3 points, this is going to create a bending stress, which is tensile in nature. So this black line here, this is the applied stress from this loading here. So you can see that this is tensile in direction. So what shot peening is going to do is it's going to put in a residual stress in the opposite direction. So the shot peening stress is going to be of a compressive nature. So that's over here. So tensile stresses are defined as positive. Compressive stresses are defined as negative, just because since they're exactly opposite each other, they have a, if you will, the one is positive and one is negative. So what the part experiences is the addition of this positive stress and this negative stress. So that's this curve here. And what we're showing here is that even under peak load, again, this is the tensile stress, and there's a higher magnitude of compressive stress, such that the surface is still in a net compressed environment, even at peak load. So theoretically, this part should never fail, but the reality is it is probably going to last 3 to 5 to 10 times longer by the residual stress canceling out the applied tensile stress.
David, I had my microphone muted. When you were on the previous graph, how were those residual stresses measured?
And so these were using X-ray diffraction. And there are several companies that do that as an outside service. And we commonly use Proto, and the other company that does measurements is called Tech, and they're in Knoxville. But each of these measurements is done individually, and then they electropolish down to a depth, and they take another measurement, remove a little bit of material, and then after they do this, about 10 times, they piece the dots together to make the curve.
Very nice, thank you.
And typically, when you shot peen anything, you improve the fatigue life from 3 to 5 to 10-fold. And some people will say, that seems really strange that you hit this metal surface with these little BBs and it lasts 5 times longer. And the principles why that works is the SN curve It's also called the stress versus load cycles, or stress versus number of load cycles. So this is the cyclic applied tensile stress here. And this is a linear scale, and then it goes 20, 40, 60, 80, 100. And it's plotted against the number of life cycles, which is exponential. And then it goes 10,000, 100,000, a million, 10 million. So what it shows here is that when stress is reduced, when you're in a higher cycle fatigue environment, when stress is reduced in a linear basis, it increases on an exponential basis. So let's say we use the shot peening effect of, shot peening is canceling out some of the tensile stress, so that with no shot peening, let's say that a component achieves 40,000 life cycles by having a cyclic load stress of 110 KSI. So let's say we use shot peening to cancel out some of that tensile stress, and the part is now experiencing 70 KSI of stress. So this is about a 35% reduction in the stress, and you'll see the life quadruples from 40,000 to 160,000. And I did make a comment about a dual peen, where a secondary shot drives in a little bit more compressive stress. And of course, the more compressive stress that goes in, that's the less net stress experienced by the part. But if it goes from 70 KSI to 60, that's not that big of a decrease. But where this curve is starting to flatten out, you'll see that if you're getting 160,000 life cycles here, you're now getting close to 400,000 cycles here. And so what it's saying is that the more fatigue cycles a part has before you shot peen it, the greater the improvement. So when I was throwing out, you could get a 3x up to a 10x extension in life, the more cycles the part is getting before shot peening, the closer it's going to get to that 10x or better improvement. Okay. So everything we shot peen, almost everything we have has some type of geometric or metallurgical stress riser. So in these ball studs, this radius underneath the head here acts as the high stress area. This is a large engine crankshaft. You can see a fatigue crack going from this, starting in this web, going across the oil hole to this web. I don't know where the fatigue crack started, but the knock sensitivity are going to be this radius and this oil hole. And of course, you can see the crack going right through all of them. Now, I'd say with springs, they don't so much have as like a real obvious notch, but if we take a compression spring, when that spring is coiled, there is residual tensile stress from the coiling operation inside that compression spring. And that's where I can kind of consider that like a metallurgical, in that there's not a really severe radius or something, but there is residual tensile stress created from a prior operation that's going to accelerate the failure. So what this shows is that this plots fatigue strength. Of course, we want our parts to have more strength, and we want our parts to last more cycles. So what this shows is that for parts that are not shot peen, which is this blue curve here, in some situations, I forgot to define the horizontal axis. This is ultimate tensile strength, would be the black numbers, and the red numbers are the corresponding Rockwell C conversion. So of course, 190 KSI tensile strength has about a 42 Rockwell C hardness. So in some situations, as the metal gets harder, you become more prone to a brittle failure. But now, in this example here, it shows that some of your optimal hardness might be around 45, 50, because this has a good blend of ductility and strength. However, when you shot peen something, which is the blue curve, I had mentioned that as the part gets higher strength, the proportion of the amount of compressive stress you get is proportional to the strength of the surface. So as the surface is getting harder and stronger, you're getting more compressive stress from the shot peening. And I should have mentioned this curve first, which is the non-shot peen. But what it shows here is that when you shot peen parts, it's better to have the material be harder and higher strength. So you guys probably notice when you go to higher strength spring wire, you get better results. And then when you shot peen that, you're getting more compressive stress from the higher strength spring wire. So you should get like a double bump in performance if you compare a lower strength spring wire to a shot peen higher strength spring wire. Any questions or comments? So in most situations, most of our customers are interested in getting more life from the shop peening. And in some cases, our customers are interested in putting more load through the part. So typically you can increase the load on the part about 10 to 30% and get the same amount of life as the non-shop peen situation. So this example here just shows, let's say that this compression spring, as throughout its loading here, it goes under full deflection, the peak stress is 100 KSI. So let's say that this situation here gets 300,000 cycles. So now with shop peening, what you can theoretically do is increase the loading on the spring. So let's say now you're compressing it further, such that your peak stress is 30 KSI. So you're putting 30% more loading on that spring. Theoretically, you might be able to achieve the 300,000 cycles you were getting under the lower stress loading. And this is probably the industry that's probably most interested in this are gears and shafts and gearboxes, because when you think of the transmission of your car, it's rare these days to ever think of a failure in that transmission, but you continually hear about, hey, the next model year has 5 or 10% more horsepower going through that transmission, et cetera, et cetera. And shop peening is one of the tools they use to drive more horsepower through that black box. Okay, so most of what we do is a single peen. And so this thing here is a 230H, which is a very common shot. This is a 23 thousandths diameter hardened steel shot at 16 to 20 thousandths A. And that's this left one here. This is a 30x magnification, which is pretty good size magnification. You can see the individual peening dimples. And for situations where you want to get more life without a lot more expense, you can shop peen it a second time, which we call a dual peen. So in this case, it was shop peen a second time with a media that's about half the diameter. So this is an 11 thousandths diameter at a lower energy. What you'll see is that the highest peaks from the first shop peen get pounded down, so you have more of a refined surface finish. But the main reason to do a dual peen isn't to improve the surface finish a little bit, it's to drive more compressive stress in there. And usually when you dual peen something, you can about double the life of a single peen. So for example, let's say you had a spring that was getting 80,000 cycles without any shop peening. With a single peen, it went to 80,000 cycles. With a dual peen, it might go to 800,000 cycles.
And when you dual peen, the compressive stress, that's mostly affecting the overall curve or affecting primarily the surface?
Primarily the surface. So for example, we'll see that the initial let's assume this is a single peen here. The surface here is about 85 KSI compressive. If you did a dual peen, you would only change the 1,000ths closest to the surface, and this peak stress could very likely go from 85 KSI up to 115 KSI. So that's almost like a 50% improvement in this example of compressive stress. And the residual compressive stress at the surface has a significant effect on fatigue life. So if I were to draw the dual peen, if I were to, let's just say I take the curve here, just extend right there, you know, the second peen doesn't change the bulk, the peak stress or the depth here. It just changes the surface compressive stress.
Thank you.
So the second pin must be a smaller size than the first one?
Yeah, half the size.
Yes, that is the general procedure, is to select a smaller shot at a lower intensity. Okay, so this happens to be a compression spring. So this one here looks at a before and after. So if you guys can envision this black curve not existing, what this pink curve shows is the residual compressive stresses as a part of the coiling process. So you'll see there's 50 to 70 KSI of residual tension from the coiling. So whatever applied stress the spring has, you have to add this residual tensile stress. So let's say the spring has a cyclic tensile stress of 100 KSI. You actually have to add on 50 to 70 when you add the residual plus the applied for the total stress. So now when you shop peen, now this is going to disappear because the shop peen is going to convert. This residual stress gets converted into this. So imagine this pink curve disappearing. So with shot peening, in this example, you have 100 to 150 KSI of compressive stress at the surface. And what happens from a life standpoint is with no shot peening, this spring was getting about 80,000 cycles. And then with shot peening, it goes over 500,000. And as Richard says, that this compression spring would fail at that ID because of these residual tensile stresses are in the ID after coiling. Thank you. And here are just some other generals. Here's just some different spring geometries. Here's a pretty good size compression spring here. Here's a smaller compression spring. These all fail the ID. Here is an extension spring, and where extension springs usually fail is where the hook bends off the body at the inside radius. That's the most common area for that to fail. These are torsion springs. They will usually fail at the OD, where the leg meets the body. And then here's just a general wire form that acts as a spring. I think this goes into an office chair of some sort. And then gears, I'm not going to spend a lot of time on this, but this is a pretty common application. Gears can fail down here in the roots from bending fatigue or rolling sliding fatigue on the flanks. Here's some different types of gear geometry, from relatively small automotive gears up to pretty good sized mining gears. This is an agricultural gear where we shot peen the inside. And then welding is another process that benefits quite a bit from shot peening. And the reason being is that when you weld something, the weld goes down in its hottest, most expanded state. So the weld wants to cool quickly and it wants to shrink as it cools. But since it's bonded to a base material, the base material doesn't let that weld shrink. And that's why it's in residual tension. So again, here we have another residual stress graph. And this blue curve here shows the as welded condition. So in this particular example for this 1020 material, it has about 20 KSI residual tension at the surface. And so again, any applied tensile stresses are going to have to be added to this residual stress. So most commonly people think of stress relieving. So when you stress relieve, most of this residual tensile stress goes to about a zero stress condition. And now when you shot peen, you drive it into this residual compressive stress here. So let's look at this purple curve here. This metal is much softer than a typical spring wire. So you'll see the peak residual stress is about 60 KSI. And if we look at the depthing, the depth of this might be 25 thousandths deep here. And then most welds, they don't necessarily fail for metal fatigue. So if you have weld issues such as distortion or chemical mismatches or something, shot peening can't do a lot. But for the welds that are in cyclic loading, which vibration is a common one, this spring here has these metal rams that go up and down. This cage, if it will, gets mounted on the back of a truck, and then this is used to break up concrete roads. So these metal rams go up and down, and they break up the concrete so they can sweep it away. And there's over 100 spot welds on this frame here. And whenever one of these welds would fail, it would shut down a road crew. So since they started shot peening these welds here, they've reduced their downtime by about 95%. This roller coaster, of course, high safety factor. There's welds at all of these locations. So all of these spot welds are shot peened. This is another roller coaster application. So the riders sit down in this area here, and the high stress welds are up in this area. So these welds get shot peened up here. Any questions or comments? So the industry that embraced shot peening first was the aerospace industry. And then today there's a number of areas on a lot of aircraft that get shot peened. So on the aluminum, the curvature of the aluminum wing skins, it is not uncommon for the curvature of this wing, this gradual curvature, to be put in by shot peening. A good number of rotating parts, whether it's the shaft or the blades, it's common to shot peen rotating parts of a jet engine. And all landing gear on all aircraft are shot peened because they're all metal. And then, so this is a propeller hub. So if you think of like the propeller blades come out of these four bores here, this aluminum is soft. So this is what it looked like before shot peening, and after shot peening, it looks like this right here. So these are the aircraft. If you look at these Boeing aircraft here, from the 717 up to the 777, all of these Boeing aircraft have metal wings, and they use shot peening to form it. And then just like these Airbus from the A310 to the A380, again, these all use aluminum wings, and they are curve formed by shot peening. So typically it'll look something like this. So you'll see a lot of surface area with not a lot of thickness. So this will go through this machine and it will be shot peened on both sides, and it'll be shot peened more aggressively on one side. So the side that has more shot peening energy is the where it's going to curve towards. So if you kind of look, this is kind of like a great big almond strip right here. So when this is out, you know, a typical curvature will be something like this. And then the higher energy shot peening would be on the inside, because it curves towards where the more aggressive shot peen is. And for about 10 years, my company did the forming for the Airbus A380. So if you look at this great big wing skin, this curvature was put in by shot peening. And these guys are using feeler gauges to make sure that this skin checks up with these, they call it check fixtures or contour fixtures. So something, I don't know, do you guys ever run into stress corrosion cracking on springs? This is something it seems we run into more in the aerospace industry. So to have stress corrosion cracking, you need 3 or 4 different things. You have to have a tensile stress, and that can become from like residual, let's say welding, or applied like internal pressure in a vessel. So you need to have a tensile stress, a susceptible material, which what we find most commonly are 300 series stainless steel, and also high strength aluminum, and some type of corrosive environment, with the most common being chlorides in solution or salt water. And of course, you need some type of time lapse. So this era was a steel U-bend. So if you can imagine like a horseshoe shape, and then down by the feet of the legs, if you squeeze those legs together, you're stretching the outside of the horseshoe to put a tensile stress on it. So this was a susceptible material, which is 300 series stainless steel, chlorides in solution. So with no shot peening, this fails in less than an hour. And then with these 3 different shot peening parameters, it lasts more than 1,000 hours in each case. And that's because the shot peening compressive stress replaced the tensile stress that was causing failure. Any questions or comments?
Yeah, I think, David, for where we might see stress corrosion cracking is in petroleum downhole applications. Of course, when you get into that environment, then you're using more sophisticated materials. So that's where that might apply as springs.
Okay, good point. All right. And so engine parts are good applications. When you think of a vehicle, any vehicle, whether it's an off-road tractor or a car or pretty much anything, engine parts and suspension parts are very good high cycle fatigue applications, because every revolution of the engine is a load cycle. Here happens to be a very large crankshaft right here, and there's all kinds of geometry changes between the mains. They have the radii here, the pins, they have the radii on both sides, and then along with crankshafts and lots of geometry change are connecting rods, because every engine revolution is a load cycle on connecting rods. Here's a medium-sized connecting rod here's a pen for reference, and then here is a much larger connecting rod that's almost as big as a pallet. And these will typically fail on this outside radius here, or in the I-beam section where it's the material is machined out. And then drive shafts are another good application. Drive shafts, every time you hit the accelerator in your car, your drive shaft is going through a series of load cycles. Here you can see the fatigue failure here. So you see the 45-degree crack, which is typical of a torsional type of fatigue failure. So this is an automotive type shaft. This is the main rotor shaft for the Chinook helicopter. This is a very expensive, low volume, life critical application. Automotive, of course, nobody wants their drive shaft to break, but most likely nobody's going to die. Here is a spline shaft where you can see this was not shot peen, and there is a fatigue crack coming out of the root radius. And then we have pets. This cat here was down to 3 lives, and then we shot peened it. We got it right back up to 9 lives again. So this is the slide I need when I give this presentation after lunch. Usually when I have the first presentation after lunch, I get a sleeper. This is what wakes them up. So a couple of things you could shot peen you might not think about are keyways. When you think of a keyway in a shaft, that bottom radius tends to be a very small radius, which means a very high notch sensitivity. And we have small shot media that can get into that small radius. And another are threads. So this example, these are male threads. And so whenever you shot peen these, you'll generally, it'll be a lower energy shot peen, either with glass beads or a small steel. And the main goal is to get complete coverage on the thread area without destroying the thread profile. But threads tend to be pretty notch sensitive, and typically on a male thread, if this thread is like the engagement disengagement zone, the top part of this acts as kind of a lever to go back and forth, and then the engagement disengagement thread is where most of the stresses, where usually the fatigue failure will happen. So the 3 shot peening control that I'm going to cover, I'm going to go maybe a slide or 2 slides in each of these. So I'm going to go through these one by one, so there's no need to have to remember this. But the first thing is the media control. So whenever you do controlled shot peen, you want to have all of your media have the external surfaces be essentially round. And what you do not want is you don't want the surfaces to have sharp corners on it, because if you are throwing this media at high velocity, these sharp corners in this media can put stress concentrations into your parts. So this is an exaggerated example, but this is a 100x magnification. So here is a shot peen with using high quality media. You'll see no abrupt changes in the surface. Now, if you have softer metal and broken down media, that shows how much you can damage the surface, where these stress concentration sites are probably going to be a future fatigue crack starting at that surface. So all of our shots have what we call it as a classifier, and this filters and separates shots through 2 different stages. Up here are vibrating screens that they will separate the shot into different sizes, and then once it gets properly sized, it will go down into this area, and then it'll once it gets properly sized, the shot will come down this channel, it'll hit this cone, and it'll begin to roll. So a good high quality shot will gain enough velocity to go from the inner flight to the outer flight. And so that shot that goes to the outer flight, we will reuse because it has a good shape, but the broken down shot doesn't roll very well. So it'll stay to the inner flight, and we throw that away or recycle it or whatever, but bottom line, we don't reuse that shot. Okay. So here's just an example of like really low quality shot and what you do not want to be using. And if you don't do a good job of maintaining your shot, it's eventually going to look like this. So what we do is every 8 hours, according to the mil spec, the shot has to be inspected. And if there's a certain percentage of broken down or undersized media, that shot has to come out of the machine and go through that classifier to remove the undersized and broken down media. And this is exactly how you do not want your shot to look right here. And this is exactly how you want it to look. And so when you use almond strips, what you'll do is that before you run a load of parts, you will process almond strips, and the almond strip has to be mounted into a block of some sort. And then this should predictably distort, kind of like an kind of like forming a mini airplane wing. It will distort towards it will arc towards the shot peening, and then we measure that with a dial indicator right there. So using the A strip, which is the most common, this 50 thousandths thick strip, if it's showing 15,000, we would call that a 15,000th A intensity. And for some components that are more critical, the best almond fixture is a spare part. So wherever you see these blocks, 1, 2, 3, 4, 5, this is where, of course, almond intensity is being measured. And almond intensity is measured before a load of parts, so that if it's not reading properly, you can make some changes to the process. And then the same almond strips are run at the end of the lot, so that you want to verify that the settings of the machine haven't changed. And if anything changed, you'll be able to identify that with an incorrect almond strip reading. So a spare part is great. In some cases, like this turbine wheel, it's difficult to get a spare turbine wheel. You are allowed to manufacture a representative geometry. So wherever you see these blocks here, that is where they're interested in measuring the shot peening intensity. So the last one is the coverage. And so every one of these shot peening impacts, of course, leaves a dimple. And you could say that there's a, full shot peening compressive stress here. But when you have areas that are missing shot peening coverage, you have 0 to reduce shot peening compressive stress. And in our shops, we don't let anything leave without complete overlapping shot peening dimples, and we call that 100% covered. And if you guys see on a drawing 200% coverage, what that means is you determine the time to achieve 100% coverage, and then you run the parts for twice that long. And then the last thing is coverage. And then that would be, what percentage of the surface area is obliterated by shot peening dimples. So this is aluminum. It's a soft metal that it's easy to see the dimples. You can see completely overlapping dimples. So this would be full coverage. Wherever you see the flat spots here, you do not have coverage. So this might be 40% covered, if you will. And then you would have to identify at how long you shot peen that to have complete overlapping dimples for 100% cover. And so some materials like this aluminum, it's easy to see visually. And other times when you have large amounts of surface area or very hard metal, or sometimes the inside of blind holes, it's more challenging. So we have a liquid tracer dye. And what happens is when you apply the dye, it goes on, you apply, you let it dry, and then under a black light, it shows up as greenish white. So when you see a solid, all of the dye, there's no shot peening coverage. And then as you increase shot peening coverage, each impact is removing the dye. So as you get more and more coverage, more and more the dye is gone. So this is about 65% covered, 85% covered. And then this has 100% coverage right there because all of the dye has been removed. So we use this dye for setup purposes. Are there any questions or comments? This really doesn't apply in the spring industry, but we also offer on-site shot peening. In some situations, it's just a really quick get in, set up a plastic tent, shot peen a localized area and get out. And then if you've got more repeating geometry, we also have programmable robots for doing the repeat geometry. And then in some cases, we do some glass beading for non-fatigue or some shot peening. So this metal cylinder with these burn lines here where it was welded, if you glass bead, it leaves kind of a frosty appearance here, a frosty type appearance. This pellet, this mold makes plastic pellets. And by shot peening this aluminum mold, it will put a texture on the plastic parts. And that texture will hide a lot of nicks and dings and flaws. And then here's some examples of where people just did shot peening because they like how it looks. The Louvre in Paris, we shot peen these support brackets just because they like that textured look. Here's a shopping mall. So you can see the handle. This is before texturing. This is after texturing. Here's a handle right there. And they did more stuff like all the brackets and stuff. But if any of you guys have like a metal flower pot and would like a texture, we could certainly do that for you. And then we are a worldwide company. We currently have, I think, between 65 and 70 locations doing different treatments between shot peening, different types of coatings, laser peening, and then we also have do analytical services at 5 locations. So that is the presentation. And if you have any questions or comments, I'm happy to take them.
Questions, everyone? issues you've had maybe with shot peening if you're doing shot peening in-house, or issues you might have seen outside, or success stories with shot peening?
I have a question here. With torsion springs and extension springs, do you find you have trouble with those because shot wants to bury in the coils at all, or do you have a way around that at times?
If it is a geometry that's prone to stocking shut in the coils, I really don't know a better way. It's frustrating because you do springs in bulk or batch to keep the cost down, and then you're getting shot stuck in some problem geometry. It's no doubt it's frustrating, but it is hard to keep it out of there. Generally, what you could do is you could try to go to a different shot size. Sometimes, of course, you see it, in the wire, there's like a little pinch point that the media can get stuck in there. And if you change media diameter, the next diameter might be less prone to getting stuck in there.
Understood. Thank you.
But it's not a guarantee, but hopefully it's less, it makes it be less of a headache. The other thing that's common to spring companies run into is they say, I have a compression spring. It has a tight tolerance on the spring load or spring rate, and then I shot peen it and it goes out of tolerance. So shot peening will reduce the spring load about 2% for most springs. So you can design the spring on the high side, knowing that shot peening is going to lower it about 2%. And the more aggressive the shot peen, the more the spring load is going to drop.
Does that apply to my internet burped a second, David. Is that for compression springs or extension springs or torsion springs were you talking about with the load decrease?
Compression springs come to mind first, and where I think it would apply to like torsion springs is in the change in angle. I don't have a lot of good data, but I would bet that shot peening is changing the angle on a torsion spring, and the more aggressive the shot peen, the more it's going to change that angle. So generally, reducing the shot peen is usually a practical solution for those.
Okay, there's a question that came in the chat. Should we use softer shot on an extension spring since they tend to fail at the tip?
So we don't use softer shot for those. And when you say the tip, meaning like the end of the hook, if you will.
He's typing.
Okay. Yeah, I guess I haven't experienced that. I will say that yes, if you are experiencing that, you might want to try a regular hardness shot, because what happens is that for both an extension spring and compression spring, an extension spring, when that coil bends off the body, the internal radius is in residual tension, the same way as the inside of a compression spring. And one of the biggest reasons why shot peening improves it so much is that residual tensile stress gets converted into residual compression. And if you use that lower hardness shot, it's still going to convert that residual tension into residual compression. So my thought is that you're going to get a pretty good fatigue, probably not as good of a fatigue improvement, but still a very nice fatigue improvement. If that solves your problem with that tip, I would then go to the less hard shot.
And I think with extension springs, the reason that we shot peen extension springs is to address the stress in the hooks. We're not going to see an advantage in the coil body so much on an extension spring, but we are going to see it at the hook.
All right, Chris, did I address your questions?
Again, my internet burped. I apologize. And then another question was, how do you select the media size based on the spring material size?
We normally use the wire diameter to generate a shot peening call out.
Yeah. And what we've said, Dave, in our classes is you might start with something that is 10% of the wire diameter. Is that a good number, or is an average?
So generally you want to be able to predict, yeah, that's a pretty good. So what I would do is if you look at, let's say, the diameter of the spring, let's say it's 100,000 to keep the math simple, and then consuming about 12% of that cross section in compressive stress is logical. So when I say, 12% of 100 thousandths is going to be 12 thousandths, and a spring is going to get shot peen on both sides. So you'd want to design a shot peen call out that's going to have about a 6,000 depth of compression. And it's not like super, super, super accurate, but it should get you pretty close pretty quickly.
Good questions. Thank you. Additional questions? Either via the mic or via the chat? Well, if there are no further questions, I'd like to thank you for taking the time to participate in this shot peening class. We hope you found the material to be useful in what you were looking for. As a reminder, please take a moment to fill out the class evaluation form, and special thanks to our instructor, David Breuer, for presenting this class. Thank you again for the opportunity to present this information to you. Any final words, David?
No, Rick, I've always enjoyed shot peening springs, going back when I first started like 29 years ago, Wisconsin Coil, they were the spring shop that was closest to me. They were pretty active in like SMI and whatnot. And I recall doing a technical fatigue study with those guys, and they did a lot of fatigue testing, and we did a lot of different shot peening when we measured the residual stress and correlated to difference. And I've always enjoyed the spring industry.
Okay. Again, last call for questions. And if there are no further questions, wait a minute. Oh, just a comment is that we have about 20 people here at CTI listening, and apparently they like the presentation.
I appreciate your time, and I'm glad that looks like we're going to come in exactly 1 or 2 minutes under the hour.
Excellent. Again, thank you, everyone, and hope you have a great rest of the day. And again, David, thank you so much.
Okay, appreciate it. Appreciate it, Rick.
Bye-bye.
Okay, bye, guys.